We are on chapter 23, talking about alternating current circuits. As you know, the alternating current uh, is an important part in our daily life, and the circuit is built with resistors, capacitors, and inductors, and all these combinations. And the flow of charge swings back and forth and continues to change the polarity in an alternating current generator. Okay, so that's how basically it is. I'm not going to go to details of how the generator works, but now let's go to um, what happens to a circuit with a capacitor and resistor. Look at this. In the circuit we have with 25, where we talked about in chapter 20.5 we talked about the RMS value and RMS for current as well as for the voltage. Okay, here we have similar way V equals IR or V equals in RMS wise VRMS equals IRMS times R. R is the reactance which is same value as the frequency changes or the voltage changes, it doesn't change. Look at the figure you have 23.1, the graph of reactance versus frequency. It is in a horizontal straight line, and then we can arrive writing down the equation VRMS equals IRMS. VRMS equals IRMS times XC. XC is replaced for R, and that is known as capacitive reactance. Like resistance, XC is measured in ohms, and experimental data has been showing that XC is inversely proportional to F, where F is the frequency, and C also. So both F and C are important part in defining XC. Now we'll go over the graph 23.2, 23.3, and 23.4. Look at here, the resistance doesn't change with change in frequency. It remains the same as you see in this graph here. Now this is a circuit with a capacitor, and you have alternating current. Here the capacitive reactance XC is inversely proportional to the frequency because XC equals 1 over 2 pi fc. This is a very interesting graph, as you would see, how the current and the voltage behave when you plug into a AC source. Look at the graph here on this side. On the x-axis, you see the voltage actually defined as, see, it starts from this point, red goes, and that's the current. Voltage actually starts from 0, back to negative, again 0, going to the max. So it shows that current is leading, they are not in phase, and current always leads at least 1/4 of a cycle by the phase angle of 90 degrees. Excuse me. Now we're going to inductors. We talked about this in self-inductor part in the previous chapter, which is 22:9, where we had V equals negative L times delta I over delta T. Delta I over delta T is the rate at which the current changes. So we can write the similar way, the same way, where XL will be replaced in that equation where we have V equals IRMS or VRMS equals IRMS times XL, where XL is defined to be 2 pi FL. Okay. Now let's go over the graphs. What happens to the reactance, which is inductive reactance. All right. The graph on the top here, the simple resistance where you register there, both the current and voltage are in phase. They start at the same time when you turn on the circuit, but it's not the same for the capacitance. Here, as you see, L, which is IL, this is VL. So the current is leading compared to the voltage. Voltage is actually lagging. Now you can see XL is the inductive reactance in this graph. The circuit is a simple inductor, and XL is directly proportional to F and L, or rather I would say F to XL equals 2 pi FL. So XL is directly proportional to frequency. Now you look at this graph here. It's a straight line graph. As XL increases, frequency increases. If frequency increases, XL also increases. Okay. Now the instantaneous voltage and current In this circuit, um, is shown here in this graph. Red is the current and voltage is blue. As you see, the current lags behind the voltage with a quarter of a cycle or by an angle of 90 degrees, as you see in the graph. This phase diagram is more clear. This is your current, that's the voltage. Now let's look into a circuit containing excuse me, resistance, capacitance and inductance. So you have resistor, capacitor and inductor, all three connected in series on page 655. Okay, so look at the graph we have. From the graph you will see how the relationship in this equation, like V0 equals VR square plus VL minus VC, or in other words, you have VRMS square equals V square plus VL minus VC. Okay. Now we can write in terms of RMS, VRMS equals IRMS R square plus XL minus XC in parentheses squared. Now look at all these three relationships I wrote here, which is VR, VC and VL. From here we derive this equation here on the top. Now this factor you have, which is R square plus XL minus XC in parentheses square under root, is known as Z, or the impedance of the circuit. And from there you can also derive tangent phi equals XL minus XC, and power will be VRMS IRMS multiplied times cosine phi. So Z is known as the impedance of the circuit, as I said. Now let's look at the graphs. So all connected in series here. Now look, impedance and this inductor both are in same line, as you see in this graph, which is talking about the V, or the voltage. Current is on this line. Okay, they are also, both the currents are in phase. This is a expanded form of the graph from where we can calculate using Pythagorean theorem the impedance. Okay, we have VL, VC, both are in not the same direction but they are opposite, and which is giving rise to VL minus VC, as you see here. We can consider this as a triangle here and figure out the equation. This is a simple math which I just copied from the book. It's the opposite to the same page on left hand side, so you can go over yourself how to figure out the tangent phi. Now the behavior of current and voltage gives rise to a condition which is known as resonance in a RCL circuit: resistor, inductor, and capacitor. Okay, now as you go to this figure here, 2317 and 2318 on page 661, when impedance becomes R or resistor, then XL equals XC. So we can equate this here as you see, 2 pi F0L equals 1 over 2 pi F0C. They are equal. Or inductive reaction, capacitive reactance, they are equal. Now from there we find out F0, which is 1 over 2 pi under root L times C. This factor 1 over 2 pi under root L times C is known as resonant frequency. Go to figure 17 and 18 now. Now on 17, as you see, the impedance, this is the blue one, is the impedance of the circuit, and here you have RMS current, which is the red one, at different frequencies. Frequencies marked here in the x-axis. Now look, when the impedance slowly comes down and down, the current goes up. Okay, so the current is the maximum here at this point. Here, this is the point here. Impedance is minimized. Okay, so this point, as you see the dotted line, is your impedance related frequency again, because it is RLC circuit, and this is F0 is resonant frequency. Now this shows you the effect of resistance and current in a series circuit with RCL. Okay, here your IMS, IRMS, this is your resonant frequency, this is the frequency line. Large reactance, this is the small reactance. I will mention to you real quick how the capacitor looks like. Two metal plates, one is positively charged, other negatively charged, and you're connecting it to an ammeter to measure the current. So the flow of charge in a capacitor controls the current. You can read yourself, and you have done already the experiment on the capacitor also. This is a RAM chip which is used in transistor capacitor combination in computer memories. So this is just for your knowledge. It's not been included for physics 112. This page is 528, is an important page where we define Q, the charge, equals C times V. Okay, and capacitance unit is farad. That's what you see there in that page. So you can review yourself. That's all I would say for this chapter. You need to prepare very well. There are hardly 3 equations here. One for RC, then RL, then you have RCL, which is resistor, capacitor, and inductor. So you have 3 basic equations will be used to solve problems. I'll try to post some problems as per your reference next week. In the meantime, you can go over the examples you have in the book. Okay, it relates to all these equations. Okay, thank you. I'll talk to you again for the next chapter.